Okay, hello everybody. My name is Ramkrishna. I am from the Department of Electrical Engineering, IIT Madras. So, welcome to the third module of the lecture series on linear systems theory. So far, in the previous in week 2, we have covered some basics of linear algebra, starting from vector spaces to normed vector spaces to what is a linear transformation and how a linear transformation essentially has a matrix representations. And all this we need because we want some nicer tools to analyze systems at hand, which we write in the state space form. So, we just continue our discussion on the properties of matrices and vector spaces. First, we will just look at some very basic types of matrices. Much of this would not be surprising to you, some of them might be even like intuitively clear. So, we just run through those definitions just to maybe make the slides or the course a bit self-contained. So, we all know about square matrices where the number of columns and the rows are the same. Rectangular matrix would be of like size m cross n, where m can be less than or even greater than, and so you can have a matrix which has more number of rows than columns and vice versa. So, even though much of our analysis would be restricted to square matrices, and therefore, we will spend a little more time on looking at properties of those. So, first is the identity matrix. We will denote it as IN, which means it is like a n cross n identity matrix. So, typical I2 would look like 1 0 0 1, and then we will just try to memorize this notation. Symmetric matrices, A would be equal to A transpose, and I think we all know what the definition of for transpose of a matrix is. Similarly, we have skew symmetric matrices where A is the negative of A transpose. Say a simple example would be something like this is a skew symmetric matrix. You can just look at just substitute and look at it in terms of each elements of the matrix. Diagonal matrices where so the by definition it says Aij will be equal to 0 for all I not equal to j. So, here Aij essentially is would represent each of the element of a matrix. Say for example, if I take a 2 cross 2 matrix, this would be A11, A12, A21, A22, and by the definition of diagonal Aij would be equal to 0 whenever I is not equal to j. So, this here I is not equal to j, I is not equal to j, and therefore, A12 would be A21 would be 0, and then the diagonal matrix would just look like this. I am like very straightforward. There is nothing really to explain much here. Some more definitions of what is a lower triangular matrix. Again by definition it says Aij equal to 0 whenever I is less than j. If I just look at this, what are the cases when I is less than j? There is this one. So, a matrix lower triangular would be something like this. Or in general, if I have a larger matrix, I have the diagonals here. So, a lower triangular matrix would mean that all entries to the right of this diagonal, if you can call this the right direction, is 0, or this is the actual definition. Similarly, in an upper triangular matrix, Aij would be 0 for all I greater than j. So, this is a case when A21 would be equal to 0, and the upper triangular matrix would look something like this: A12, a 0 here, and A22, and we are not really worried about what is sitting on the diagonal. And in an upper triangular matrix, you will have all the entries to the left of the diagonal are 0. So, this is lower triangular, and this is the upper triangular. And of course, the last thing is that of an orthogonal matrix where A transpose is the identity of appropriate dimensions. So, whenever we just say identity, we will make sure that we are working with the appropriate dimensions. Specifically, when I need n, I will say In is the n cross n identity matrix. Something which is important, and we will revisit this concept a lot of times during the next few weeks of lectures. One is called the change of basis. If you remember a bit of state space analysis, if you do not remember, it does not matter, we will do it all over again. Change of basis essentially means how do I change, or it is a direct implication on how do I change from a controllable canonical form to an observable form or a diagonal form or so on, or given any state space representation, how do I go about deriving one of those canonical forms. And the basis of that, or the mathematical tool for that is what we call as the change of basis. And what is basis? Well, basis, if I look at the standard basis for a 2-dimensional space, it was the 1 0 0 1. And what we also did a little example is that given a vector space Rn, the basis may not be unique, right? And therefore we have to emphasize, okay, what is the thing that causes the change of basis? How do I go from a set of a standard basis to some other basis, right? So we will spend some time on that, and also as the lecture progresses today and further this week's contents, we will try and slowly relate to the state space representation of systems as and when needed, as and when it might be a little obvious, just to make a little link of the kind of tools that we use here and how they are actually going to help us throughout the rest of the course. Okay, so what is a change of basis? It refers to a transformation which transforms coordinates of a vector from one basis to another basis. Okay, so transformation, I am talking of linear spaces, and this transformation therefore essentially will look like a matrix. Okay. And why can we do this, or why is this important, is because the set of basis vectors are not unique, and this actually helps us a lot, that the set of basis vectors is actually not unique. I mean, throughout our coordinate geometry we just look at the standard basis, right, and there I am not sure if we ever encountered situations where we had to write in different bases, but here it is very important. Okay. So the thing that we will exploit or try to analyze more is the property that a vector space can be represented using many different set of basis vectors. Okay. As I said earlier, these have their own advantages, especially in the course. Right? So this is not just very abstract thing that we are going to learn, but this is something which has direct implications on the control related concepts that we will do later in the course. Okay. So, what represents now the change of basis, or how do I go from one basis to other? It actually turns out to be a very simple exercise. So let us start with two different bases. So how do two bases relate? Well, I just take two arbitrary bases. One of them could be the standard basis for a Rn. It could be any of those, right. So the transformation exists independent of what. So let me just take two bases B and C with their individual bases being from B1 till Bn. The n vectors which represent, or which are set of ordered bases for this vector space V. Here it's like, because you have n, this could be like Rn. Okay. So B1 till Bn. So this means that any vector in Rn can be written as a linear combination of these vectors B1 till Bn. The same vector can also be written as a linear combination of this basis vector C1 till Cn. Right? If you remember what we did for the basis vectors, right. So we were talking of linear dependence, linear independence, and B1 to Bn will form a set of bases if any vector can be written as a linear combination of these vectors. Okay. So let us start with x, a vector x with its own coordinate representations x1, x2. So what was the coordinate representation? So given x, I will have, if I can write this as x1, x2 all the way till xn. This is a coordinate representation of a vector, which can also equivalently mean that I am writing this as x1, say the basis vector is b1 till xn bn. Okay. So let x be this coordinate vector, be a vector with coordinate representations xb and xc. And the same vector can have different coordinate representations depending on what basis we choose. Okay, what does that mean in when I write it down explicitly? So, this vector x with xb as a coordinate representation with respect to the basis b can be written like this, right? x1b, where x1b till xnb are the individual coordinates for this guy xb. Similarly with xc. So, this x can be written as x1b times b1 till xnb times bn. The same vector in the basis c can be written in this way, where okay. So, what changes? Since the basis change, the coordinates will also change. So, I will have xc written as x1c all the way till xnc. Okay. Now, these two are the same vectors. If I draw it on a sheet, I think they will look the same. You can just do it, just check by yourself that these two are essentially the same vectors. Okay. So, in matrix representation, I can write this b1 times x1 all the way of something like this. Okay. Similarly with this one. Okay. Now, let me call this matrix, which I already called this way. This is b and this is c. So, what I have here is b times xb, the vector xb is c times xc, right, in standard, if I just write it in terms of matrices. And okay, now look at this matrix, it has n independent columns. Similarly with this matrix, right, it has also n independent columns, because b1 till bn are linearly independent. Why are they linearly independent? That comes from the definition of the basis. Okay. So, now once these matrices are full rank, right. So, the rank of this will be n, the rank of this will also be n. So, I can interchange terms and write xc as c inverse b times xb, or I can also do the reverse, right. I can also write xb as b inverse c xc. So, what does this answer me? So, I have a vector xc, this one, right. So, these things, what is the matrix that transforms from xc to xb? And so, xc is written in this basis c1 till cn, xb is written in this basis b1 till bn. So, what is the matrix, or what is the transformation that takes me from one to the to other? That is simply this one. Okay. So, let me call this as P, and this would simply be P inverse, and we know of why these are invertible matrices, because of this n independent columns. Okay. So, what is this P? P represents a linear transformation f from V to V, which depends on the set of basis vectors B and C. Right. So, look at this, right. So, these are the set of basis vectors for B, these are the set of basis vectors for C, right. So, these two coordinates of the vectors xc and xb can be related via their basis vectors, given by this little relationship. It is a straightforward derivation, right. Okay. If one of them is a standard basis, say let us say b is a standard basis, then p is simply C inverse, because b is just the identity, right. So, it will just be 1 0 0 0 0 1 0 0 all the way till 0 0 0 and 1. This is a standard basis, let me call this as p. So, conversely, if C is a standard basis, then P equal to B, and this is like straightforward then to derive. Okay. So, what we understood is how to go from one basis to other basis, and this will be useful a lot. So, we will also help to kind of memorize that such things actually happen. Okay. And again, this transformation f from V to V has a metric representation P. Right. So, this f is essentially has this metric representation P. Okay, let's do a small example. This is pretty easy. If you look at the basis B, this is the standard basis as here, and C is given by this basis. You can check why these are bases, right, as a little exercise. These are actually linearly independent, and so on. So, what is xc when xb is minus 2 and 1? Okay, so we just make use of this formula. Xc is C inverse B times xb. Well, it's B is just the identity, so I am just looking at C inverse times xb. C inverse can be computed easily to be 7 minus 3 minus 2 1, and multiply this by minus 2 and 1. So, this will be minus 14 minus 3 is minus 17, and this will be minus 4 plus 1 is minus 3. Hmm? Okay. Okay, and this will be 4 plus 1 is 5. Okay, just a very trivial exercise, and you can just draw these two vectors on a graph and check that they are actually the same, and you can do a little more not really difficult, but something which involves computing of one more inverse. So, so instead of B being identity, I just gave you a B matrix which is like this. So, okay, there is nothing really special in this slides or in this example. Okay, let us do something which we would come across a lot of times, and this concept called the similarity transformation. So, let us start with two square matrices, two n cross n matrices, and by definition, and we will see why what this definition means and where this possibly even comes from. So, two matrices are said to be similar if there exists a non-singular, well, we need that to be invertible matrix P such that B is P inverse A times P, where P is called the modal matrix. Okay, we will see how that comes from. Okay. Now, these arise because a linear transformation can be represented by different matrices for different choice of bases, as we saw here, right. So, we had two bases, and so say for example, here if these coordinates had a basis given by the matrix B, these coordinates or this vector has had a set of basis vectors represented by this matrix C. So, essentially we are doing some kind of a special case of this one. So, we okay. So, these similar matrices represent the same linear transformation. So, whenever I say linear transformation, I am just talking here of some matrix A with different set of basis B. Okay. So, how do we like derive this? A matrix is similar to itself, right. So, what is the similarity transformation between P and P? So, well, I can say that this is just the identity, right. So, P equal to so, okay, so or take a matrix A and A, what is P? The P turns out to be identity. This is trivial. Okay. So, second is if A is similar to A, then B is similar to A. So, let us say that B equal to P inverse AP, right. It's, you can even write A as now P B P inverse. Okay. If I just want to write, so I will just call this P inverse to be Q, and then I can write a new relation like this, Q inverse B times Q. Okay, then all those properties of associativity, if A is similar to B, B is similar to C, then A and C are also similar. Okay. So, A is similar to B, then they have equal rank, of course, they have equal determinant, they also have equal traces, right. So, so we just do some things here. So, why this is important first from the control point of view. So, most of our examples would look like this. So, if I just say I have a system x dot t is A x t, the standard state space representation that we will substantiate a little more later. Okay. Now, suppose I were to write this in some other coordinate, these are all coordinate representations, right, x dot t, which are the states, these are essentially coordinate representations where x of t belongs to certain, say, n dimensional space. Okay. Now, let me just call something that x equal to p times z. Okay. So, I just omit the arguments in time. So, these are all this is t, this is t, then x dot of t is p z dot of t. Okay. Now, what is x dot? X dot is a x t equal to p z dot of t. So, now what I want to say, so given my system dynamics in x, how would they look in z? Okay. So, z dot, and this is always an invertible transformation, that was the necessary condition. So, this z dot or p times z dot is a x t, or p times z dot is a, what is x in terms of p? So, I will get a p z of t, or in other words z dot of t is p inverse a p z of t. So, this is my similarity transformation, right, which transforms my dynamics in certain given coordinates x to some other coordinates z. Okay. Now, all properties, if you remember vaguely, of stability were all related to the matrix A, right. So, say for example, so here I just said that, well, these have equal rank, equal determinant, equal trace. Okay, maybe one of this would be easy. So, equal rank is like easy to find out. So, a very important concept I would always look at is, okay, what is the implication on stability? And if you remember, stability had something to do with eigenvalues, or the basic properties of the matrix, right. Even if I look at in terms of my characteristic equation, the poles and so on. So, how do the poles of this system relate in x to the poles of the system in z? Okay. So, let's quickly do this, right. So, how do I find those? So, I have lambda I minus p inverse a p is the determinant of this, is my characteristic equation in z coordinates. Okay. Now, this will give me a set of eigenvalues, and if I were to look at, so what I want to establish is the eigenvalues which come from this matrix P inverse A P and how they relate to the original, so to speak, A matrix. Okay, I can write this then as P inverse lambda P inverse A P, and can do this is equal to P inverse. So, inside I will have lambda minus A. So, just to make it consistent, I just put lambda I minus A times P. Okay. Now, this is equal to P inverse lambda I minus A times P, and this is lambda I minus A, right. So, the solution to the characteristic equation would just be to equate this to 0. So, if I equate this to 0, it is as good as equating lambda I minus A to 0, and therefore, the eigenvalues of the matrix A are the same as the eigenvalues of P inverse A P. So, much of the properties remain invariant, right. I mean, it's kind of intuitive also of why these properties should remain invariant, right. Okay. So, now what does similarity transformation, or how do these relate directly to a change of basis, right. Is there a nice interpretation of this P inverse A times P? Okay. So, let us do a little scenario here, right. So, let me take a space X, could be of whatever dimension, and say it has the coordinates x b with b1 till Bn being its basis vectors. The same x has another coordinate representation xc with c1, c being c1 till cn being its basis vectors. Okay. So, what we saw is that so if I just were to rewrite this formula here, that xc is p times xb. Okay, let us rewrite that here, that x c is p times xb. So, it would mean that this p is a transformation which goes this way, this side, not this way, is correct. P times xb will be xc, right. Okay. Now, assume also that I have another space, say y, okay, which could be of a different dimension, say, and has its some vector representation here as yc, some vector representation here as yb with its own set of bases, right, whatever they could be. You can just write whatever notations you want for that. So, okay. Now, we know, say suppose there exists some transformation which takes me from x to y, and let me call that transformation to be, say, some a. Okay. This transformation should also exist here, right. So, both these spaces are y, this is x, and this x, the x on the top has some basis representations b1 till bm with a certain vector xb. Similarly, over here the x on the bottom has vector representation xc with some basis vector c1 till cn. Okay. Now, if I just look at A as a transformation from this x to y, maybe over here, right, with this under this basis. So, we always define the transformation with basis. So, let me call this just to associate it to C. It is a little not notationally correct, but let us see how. So, this is how it looks like. So, or maybe I will just call it, say, AC. Okay. There also exists a similar transformation from x to y under this basis. So, let me call this A B. So, the question is, okay, how does A C relate to A B? Okay. So, okay, now I know this, I can also define now a transformation which goes from yb to yc via some matrix Q. Right. I mean, I can just do whatever, I can even define this way, right, because this are just, so if I can write xc in terms of xb, I can also write xb in terms of xc, sorry, xc here, okay, not c here, but okay, whatever is notation, right. So, I can just go from here till here. Now, look at this carefully. So, I can always write A B as P A C times Q, right. So, this is a transformation which takes me from this basis till this basis, and it is the same of me going from this to this via AB is the same as me going via this route. So, I go from here till here, then jump from here to here, and then jump from here to here. These are exactly the same. Now, a special case of this could be when okay, let me just take a different color, when x and y are the same. Right. So, in this case x and y can also be of different dimensions. So, need not necessarily be since this is an s here and n here, this can be a different number also. So, if x equal to y, okay, so what will be this one? So, this is x, this is also x. So, with the similar changes over here. So, if I can go from x b to x c via this matrix P, then I am going again. So, y c, this is all, everything is now x, right. I can go from here till here via P inverse, okay, and therefore, I can write this as P AC of P inverse. Okay, and then equivalently I can also write AC in terms of AB. So, what we saw here in terms of, so first we try to answer the question of what is the relation between AB and AC when AB and AC are respective transformations from x to y with respect to some basis function basis vectors. Okay. So, see, so we can also have a similar interpretation of the similarity transformation. So, P inverse AP would also be similar to writing it as P. So, some other matrix Q inverse AC times Q, right. So and this is always invertible is what we know, right. Okay. To conclude, talked about change of basis and how these are related to something called the similarity transformations, and it essentially means writing down my given dynamical system or a control system in terms of in a new coordinates. We'll use this very often during the course. So in the next lecture we will talk about invariant subspaces and slowly introduce the concept of eigenvalues and eigenvectors. We would have studied this earlier, but we will just give a slightly different interpretation to this. The basics remain the same. So we will see that in the next lecture. Thank you.